In our previous topic, we learned about the way scientists communicate with one another through SI units. In topic 1.2, we will learn about how scientists handle uncertainty in their measurements and their experimental methods. Uncertainty in science is always present, so understanding how to limit your uncertainty is critical to producing clear results. To begin with, we must define uncertainty and how it plays a role in science. Uncertainty in science means that there is a range of possible values within which the true value of the measurement lies. This uncertainty can stem from many causes such as how the measurements are taken, the precision of the tools, or methodology of the experiment. Uncertainty can also come from natural variability in experimentation that cannot be controlled by the scientist. In any case, the scientist must be responsible for communicating not only the results, but also how uncertain they are in the results, due to all of the factors previously mentioned. Before we learn about the ways uncertainty can be introduced into science, we must first understand the difference between precision and accuracy of measurements. The precision of a measurement depends on the tool and method used to measure. In the example below, the diameter of a gold ball is being measured by two different tools, a ruler and a caliper. In the case of the ruler, the measurement is considered to be less precise because the person must eyeball the outer edge of the spherical shape in order to measure the length across the sphere. The caliper, on the other hand, is a tool specifically used to measure the length of an object like a sphere, and the markings on the caliper allow the measurements recorded to be more precise because there is less guessing that needs to be done by the eye of the person. In short, precision refers to how exact we can get our measurements to be. Accuracy of a measurement is slightly different compared to precision. Accuracy of a measurement is how closely our measurement matches the true value of the thing you are measuring. Knowing whether your measurements are accurate is more difficult than knowing if your measurements are precise. Because the true value of a measurement is not known, it's hard to know if you are accurate, which is why there is uncertainty in science. In order to combat this issue of accuracy, scientists rely on each other and our collective understanding to evaluate the results of experimentation. Accuracy of measurements can be assessed by comparing the measured values to expected values. For example, the average gravitational acceleration on Earth of a free-falling object is accepted to be 9.81 meters per second squared. However, when you are measuring this value in an experiment and you get something wildly different like 6.5 meters per second squared, then we can be pretty sure that your measurements are not accurate because they are not close to being what is accepted as the true value. This should set off alarm bells that something went wrong in your experiment, and you should go back and evaluate your measurements and methods to understand how your measurements were different than the expected value. Both precision of your tools used and the accuracy of our measurements plays a large role in uncertainty in science, but they are not the only factors that affect uncertainty. To reduce the uncertainty in an experiment, there are two major forms of errors that we have to reduce. One form of errors is random error. Random error occurs due to the measurement tool or due to the environment affecting the experiment. These are usually factors that are unknown to the scientist or factors that cannot be controlled by the scientist. For example, when taking a volume reading in a flask, you may read the value from a different angle each time, or when weighing something on a scale, you position the object slightly differently each time. These slight changes can lead to the measured value being inaccurate, which means it does not reflect the true value of the measurement. In order to reduce the random error in experimentation, a controlled experiment must be planned. This means as a scientist you try to reduce as many factors that can affect your experiment. This will reduce the amount of variability and reduce your uncertainty. Another way to reduce random error is to take multiple measurements and use an average of those measurements to help reduce random errors. Oftentimes, the more measurements you collect, the closer your average will be to the true value, and thus your uncertainty is reduced. This is why scientists perform multiple trials of an experiment. Another form of error that causes uncertainty is systematic error. Systematic error occurs due to the use and application of a measurement tool. This is often referred to as user error. This form of error is often hard to detect because you might think that you are doing your experiment well without knowing that you are using a tool incorrectly, or that the tool is not calibrated, or even that the method of your experiment is set up poorly. There is often no way to know that there is an error actually made. This form of error might present itself in a few different ways. For example, if you are measuring the weight of something, but the scale that you are using is not calibrated correctly, all of your measured values might be off by the same amount compared to the true value. One way to combat this error in that example would be to use multiple scales to make sure the one that you are using is calibrated. Or you can use a calibrated weight, which are very precise and accurate, to calibrate the scale that you plan to use. Another way this error may present itself is in the scale factor form, where the tool that you are using is causing the measured value to be proportional to the true value. The reason that this is so important is that if the measured value increases, the more inaccurate the measurement actually becomes. To reduce systematic errors, a clear understanding of your experimental procedure and, importantly, how to use your measuring tools is essential. Another way to evaluate systematic error is to compare the results of your experiment to others. This is often a step that is not always taken, but it can reveal a lot about the validity of scientific information if the same results can be obtained from similar experiments. Part of reducing the uncertainty in science is to be aware of how the tools you are using affect how close your measurements are to the true value. The precision of your measurement tools creates a level of uncertainty in your measurements. Take, for instance, the example of measuring the length of this piece of candy. There are two rulers that can be used to make this measurement, ruler A and ruler B. The difference in these rulers is found in how precise they are. The precision of the ruler depends on if the ruler has small tick marks to measure smaller increments of length. With ruler A, we can be certain that the length of the candy is at least 4 centimeters. But because there are no small tick marks, we can only say that the length is at least 4 centimeters. If, however, we use ruler B, we can be more precise because we know that the candy measures at least 4.2 centimeters. Those extra tick marks allows the measurement to be more precise because we are doing less guessing about the length of the candy bar. Now, to report these measurements scientifically, we must report the measurements with the precision of the device taken into account. There is a specific format we use in science to report the measurement and its uncertainty. The format is to write the measurement that you are certain of, plus or minus half the smallest increment your device measures. So what does this actually look like? Well, for ruler A, we were certain that the length was at least 4 centimeters. So we write 4 centimeters, then plus or minus symbol, and lastly, half the smallest measurement your device measures. Our ruler for ruler A only measures a full centimeter as it's the smallest measurement. So half of that measures is 0.5 centimeters. Therefore, the full measurement written out with uncertainty is 4 centimeters plus or minus 0.5 centimeters. That 0.5 centimeters is the uncertainty you have in each of the measurements you make with that ruler. For ruler B, on the other hand, which is more precise, the uncertainty looks different. Again, we report the length we measured with ruler B to be 4.2 centimeters, plus or minus symbol, but now the ruler can measure to the 0.1 centimeter mark, which means half of that measurement is 0.05 centimeters. Therefore, the full measurement with uncertainty is 4.2 plus or minus 0.05 centimeters. This means we are uncertain of the measurement up to 0.05 centimeters. Most tools will report the uncertainties in the manual or on the tool itself. It's important to look at that uncertainty value and report it with your measurements. This is a practice that all scientists must adhere to in order to report values appropriately. Remember, in science, uncertainty does not mean that a scientist, a theory, or an experiment is incorrect, Uncertainty only means that we recognize that there could be errors that were made, or that we only know the value of something based on the tools that we currently have available.